Hi everyone. I hope everyone is having a really nice Friday. I have a little bit of a different stream plan today, so anyone who follows me on Twitter knows that I've been on a I don't know, I just had kind of a random idea. I'll get to it in a second, but so this stream is gonna be about physics. um but I will also be discussing Haruhi Suzumiya. So, so if you didn't see anything I posted on Twitter, you're just kind of in for the ride. I hope you enjoyed it. If you saw on Twitter what I posted, I hope you're interested in it. But yeah, so I just want to give a little bit of a note on who this is directed towards. So this is not going to be a super in-depth mathematical type of thing. I don't really find that helpful if we don't know if we're on the same page, sort of. So hi everyone who's come so far. So hi Frolic, Evangelion, Kachel, and Gesture. So hi everyone for coming and thank you for coming. So first of all, I just want to say, I don't know where everyone is in their math knowledge, so this first part will be kept very conceptual. I really just want to give a very conceptual understanding of the physics topics that we're going to be discussing today. And yeah, so I just want to get started by saying I have on my Twitch page, if you guys go to my Twitch, you will see this coffee page. And if you guys are interested in looking at the presentation and maybe taking notes alongside it, you can download a PDF of the presentation. It is free. If you guys want to donate, you can do that as well. I'd be very thankful. But the presentation is completely free. You guys can download it if you maybe want to take notes alongside it or anything along those lines. So yeah, without further ado, I think I just want to get started by discussing I guess we're gonna start off with a little bit of an introduction, and I will move on to like the first chapter or so. So the cosplay is nothing special, I will say. It's just Haruhi cosplay, little bow. It didn't come with it. It had another little ribbon, so I just did this one myself with just some regular ribbon. But yeah, I wasn't sure if people wanted me to do it in cosplay or not, because maybe it was like a little bit distracting. But I guess people voted that they wanted the cosplay, so. But yeah, so I'm calling this series of streams Laid Back Physics. For now, we're going to be covering the topic of Haruhi, but I would also like to cover some other subjects, some other anime or other media in the future. So, yeah, so I just kind of gave it a little bit of a general title relating it to your camp, and also just relating it to laid back, as in we're not going to be discussing a lot of in-depth stuff, and we're going to keep it a little bit more conceptual. So I also am titling this, or giving it the subtitle, A Look at Physics Through the Lens of Haruhisuzumiya, in the sense that we're going to look at physics topics and we're going to tie them back to Haruhisuzumiya. So, I don't know if everyone is familiar with the series Haruhisuzumiya, but I just thought I would give a little bit of a background. So, we're mostly going to be just tackling the anime. I personally haven't read the light novels or anything like that, so it's not really going to be something that will be discussed for the time being. But yeah, so Haruhisuzumiya, The Melancholy of Haruhisuzumiya, is an anime that came out in 2006. It follows Keon, who's this guy in the right over here. I think you should hopefully be able to see my mouth. Yes. And he meets the title character, Haruhisuzumiya, at school. And she's a very outgoing, eccentric, sort of crazy girl who's bored by anything that is boring, anything that is familiar. And she's just completely... she just has a very crazy imagination and loves anything otherworldly and crazy. So Haruhi starts a club called the SOS Brigade, where they discuss and tackle also very eccentric subjects such as aliens, time travelers, and espers, which are Haruhi's 3 main interests. And just coincidentally, the other 3 people that joined the club just happened to be an alien, which is Yuki Nagato right here. Then we have Mikuru Asahina, who's a time traveler, and Itsuki Koizumi, who's an esper. So these are our title characters. Just wanted to give a little bit of a brief rundown on the show, but I assume if you guys are here, you're probably at least a little bit familiar with it. But yeah, so what else is there to talk about? So the main motivation behind this entire series was that I was watching the Haruhi opening, the first Haruhi opening, Bouken Desho, and I've noticed that there were a bunch of equations in the background, and I just looked up online, like, has anyone documented, like, what these equations in the background are? There's some other graphs that we'll discuss and so on, but, you see there's a bunch of equations. I'm like, has anyone, like, documented what these are? Not really. So I went frame by frame, figuring out what all of these are. And that's what brought me to making this series. So the goals of my series are, number 1, to document the equations that are in the background of Bouken Desho, and then to also deliver a little bit of a comprehensive explanation, more of a conceptual explanation behind the meaning of these equations. And lastly, I want to tie them together with themes of the series to maybe shed some light as to why they actually picked these equations. I also want to mention, I tried contacting Kyoto Animation to see if maybe they would respond as to, if they took a particular book in order to take these as inspiration for the background equations or something. Because there was one in particular that I really, until now, I have not really found out where they actually copied it from. But yeah, they haven't replied. Not surprisingly, they haven't replied. But yeah. Anyway, so our first topic is gonna be what I'm calling Chapter 0, because it's gonna be a little bit of an introduction as to the scales at which we're gonna be the scales of things that we're gonna be discussing in this series. So as you can see, there's Haruhi from the opening, and behind her you see a bunch of numbers with 10 to the something, 10 to the minus 20, 10 to the minus 19, and so on, and some Japanese characters. Well, these are, as we're going to discuss, these are orders of magnitude. So orders of magnitudes are a concept that help us understand and compare scales of things in particular. So we have, for example, our little Haruhi, who is going to be talking in SI units. For the Americans, just sorry, everything's gonna be in SI units. But yeah, our title character, Haruhi, is a meter point 58, which puts her in the range, or in the order of magnitude of 1 meter. So 10 to the 0 meters. Comparing that to a way larger thing, which is the radius of the Milky Way, which is estimated to be about 10 to the 21 meters. So 10 to the 21 instead of 10 to the 0. So order of magnitude 21. A lot bigger than Haruhi. And then we have another example, but something really small, which is the radius of a hydrogen atom, which is approximately, or in the order of magnitude of 10 to the minus 10. So all these little powers are what we call order of magnitude. Following that, all of these orders of magnitude typically have a name, one which is used as a prefix for SI units normally, which are, like, for example, for meters, if you have something larger, it's going to be, for example, here, kilometers, which you hear a lot, referring to distances. But if you hear, for example, about bacteria, you may hear micrometers or nanometers, so a lot smaller. And what was written in this initial background thing with Haruhi and all of the numbers were all these in words, like billions, but then there's trillions, quadrillions, quintillions, and so on. So that is exactly what was written in there. And yeah, I have sources for most of the stuff that I have here, because alongside this, I'm also writing an article that should hopefully come out alongside the last part of this series. But yeah, I just, and no, I did not look at the Japanese characters. Like I mentioned, this is only going to be focused in physics. I don't speak Japanese at all, and I am not a language person, I guess I would say. So this is only going to be focused in physics. And this is only a small introduction because we'll get to the meat of the idea. So this is going to be more so to give an introduction as to the scales that we're going to be discussing throughout the series. So if anyone knows Japanese and that's their thing, please go ahead and try to analyze that, but definitely not me. But yeah, so now that we're discussing orders of magnitude, I wanted to just quickly mention something called order of magnitude problems, also known because they were popularized by physicist Enrico Fermi. They are also typically known as Fermi problems. So these are problems that you can kind of solve with very little information. They're like approximation or estimation problems, and they often only require like very just kind of guesstimating and what they call back of the envelope calculations to solve. So I had a little bit of an example that maybe you guys can just think about so you can get a bit of an idea. And that is, how many hours does Haruhi spend thinking about something weird in a year? And the solution to a Fermi problem is then the order of magnitude. So if you think, if it's hundreds of hours, then it's order of magnitude 2. If it's thousands of hours, then order of magnitude 3, and so on. So you can have your guesses. I will just present what was my back of the envelope calculation solution for it, which would be that assuming that Haruhi thinks about something weird every single day and spends every hour she is awake thinking about something weird, if we assume that she sleeps 8 hours a day, so she's only awake for 16, then we have 365 times 16. We have somewhere in the order of magnitude 3, so a few thousands of hours a year. The kanji in the show correspond to the order of magnitude used. Yeah, like I mentioned, these are all just the billions, trillions, and so on. They also have a part where it's displayed in English. Maybe I didn't get that point across, but yeah. So that is just I don't know if the specific kanji have a meaning, but yeah. I hope I mentioned that. I hope I made that connection. There's a part of the opening where they also show it in English. I just thought the person was asking if the specific kanji had some other meaning to them, or the actual, where they came from. That is what I understood from the question from the person. So sorry if I didn't understand the question. But yeah, going back to the Fermi problems, I attached a link right here so that you guys can also check out some other Fermi problems that are quite interesting. So yeah, if you guys are bored afterwards, I recommend you to check them out. They're typically not about anything in physics. They're just kind of random, typically just random things like how many piano players do you think are in New York or something like that. So it's pretty fun. If you guys download the presentation, you can go and just click on the link. And exactly, what if she thinks about something weird while she's dreaming? That's kind of the beauty of Fermi problems. We kind of don't care, because even if you put 24 hours a day, it's still somewhere in the order of magnitude of 3. So it just really has to do with the assumptions that you're making where you justify the order of magnitude that you kind of pick. So yeah, so they're like called like guesstimation problems, where you compare orders of magnitudes of things. So I had a little bit of a pause for questions. So one question is this related to the Fermi paradox? No. These are just, they were something that were popularized by Enrico Fermi, but doesn't really have anything to do with the Fermi paradox. I don't know if there are any other questions thus far. This was probably the smallest chapter, just a little bit of a conceptual thing in case anyone hadn't heard of orders of magnitude. But if there are no questions, I think we can start with like the first big chapter, I guess. So since we were talking about how big and how small things are, today we're going to be discussing big stuff, so astrophysics. So and no, I don't think you can cite this presentation as a lecture. I am not a lecturer. Sorry. But yeah, so today we're going to be discussing the astrophysics equations that were in the Haruhi opening. So I'm just starting off by a quote by Haruhi. So, I'm Haruhisuzumiya from East Junior High. First off, I'm not interested in ordinary people, but if any of you are aliens, time travelers, or espers, please come and see me. That is all. So Haruhi mentions aliens, which brings us to our first equation, which is the Drake equation, which is shown right here. It's a little bit blurry, but I will rewrite it in just a second where you guys can see it a lot better. So the Drake equation was first proposed by scientist Frank Drake at conference on extraterrestrial intelligent life held at the National Radio Astronomy Observatory in West Virginia, and this was back in 1961. The concept of alien intelligence and like alien civilizations was something that was known, or not known, but was discussed at the time. Like, people thought about it, but it had never really been put into an actual equation, which is what Frank Drake did, because physicists just love equations. They love seeing something that they can actually grasp with numbers. So that made it a very popular concept at the time. So we're going to be discussing each of the components of this equation and what they actually mean. So, N is the number of communicative civilizations there are in the Milky Way. So this is what Frank Drake wanted to talk about. How likely is it, like how many civilizations are there in the Milky Way that could communicate with humans, basically, is what he's proposing. So he's kind of a little bit, he's a little bit like Haruhi. Like, this is something Haruhi would certainly think about. And he basically split this up into a few different factors. So starting off with the astronomical factors. First off, this R star, which is the rate of star formation. Then, so basically, how many stars do we see being formed in a given year or a given time frame? Next is the fraction of these stars that are formed which have planets orbiting around them. So per star, how many planets do we actually see? And lastly, how many of these planets have environments that are suitable for life? So if we're talking about we want to find an alien civilization, we have to first think about how many planets there are out there and how many of them have environments in which life could actually develop. This is these planets that have environments that are suitable for life can often be called that they are in the Goldilocks zone of a given star, meaning that they are orbiting, that they are in an orbit where they may get like proper heat from the star, kind of like where we are on Earth. If we were to move to Mercury, we would burn. If we were to move farther away, then we would be too cold. So it's what they call the Goldilocks zone, is just right, like the Goldilocks story. The next factors that he discussed are the biological factors. So first off, which of these planets that are suitable for life has life actually developed? Because we've also discussed that even if you say that a planet is in the Goldilocks zone, that life could actually develop there, in theory, we don't know if life actually developed in there. So we have to kind of guess, or we will discuss this in a second, but we have to know what fraction of these planets in which life could actually develop has life actually developed. Because the factors can be right, and still life may not actually develop. And then Fi, which is the fraction of those planets in where life has actually developed. Thank you for following Microlink. And then the fraction of the planets in which intelligent life actually evolves. So which of these planets in where they have an environment where life can develop, life has actually developed, and the life that developed there is intelligent life. And then we have our social factors, which are which of these intelligent civilizations that developed actually have radio communication and could communicate to over interstellar distances, so where we could actually capture their communication that they are sending. And then the big L, which is the length of time of this civilization, basically. For how long is this civilization able to send detectable signals into space? So obviously this equation, it sounds very beautiful, it sounds very nice, but there are a lot of criticisms about it. If you guys are interested, I definitely recommend this paper that I cited about the Drake equation in context, but I'm just gonna brush over the surface of a few of the factors the people consider very critical about this equation. So in particular, the estimation of a lot of these biological and social factors, it has huge uncertainties. We're basically guessing which portion of these planets could life actually develop when we only have one example of a planet where intelligent life has factors that are very hard to even estimate at all, having only one example in the entire universe that we know of. And then also, even some of the astronomical factors that are more well known do still vary depending between models. Also definitely recommend these two papers where they show some of the criticisms, but in essence, obviously a lot of the criticisms rely on, if you can't even guess how many stars, what's the rate of star formation, the rest of the factors that you're talking about are a little bit bogus. So this is not a super serious equation in the sense that people think about the numbers a lot, but people like guesstimating things, and it's fun, it's fun. So my takeaway from this equation is basically that more than helping us solve the equation of how many intelligent civilizations there are, it really is just more so asking a question itself. more so than telling us any answer. So I personally just come away with, like I said, my takeaway from this equation is basically that is more so just posing an interesting question and encouraging other astrophysicists and astrobiologists to discuss the possibility of being able to find life elsewhere. So yeah. And I think this is probably something Haruhi would do, honestly. So if anyone has any questions in this, please let me know. This is probably the most, I don't want to say bogus, but the most unserious equation that we will consider. This is just kind of a silly one that is funny to talk about. But yeah, so if you guys have any questions, please let me know. Yeah, this seems to be built on a lot of assumptions. Yeah, if you go over some of the papers where there's a lot of the criticisms, they cite different ranges, and the different ranges for the solution of how many civilizations there are ranges from like hundreds to thousands to tens of thousands. Like, it is really something impossible to actually have a very clear idea. So it's just kind of a silly equation. But the next one that we'll talk about is it's a lot more interesting in the sense of I'm gonna show you more data. more real data. But yeah, I hope you guys are interested in that. So if there are no questions, we'll move on to Hubble's law. So I'm sure you've heard about, for example, the Hubble Space Telescope. This was all named after this was all named after scientist Hubble, and here is the and I just wanted to first discuss, so Hubble's law basically talks about expansion of the universe. So I wanted to tie this into Haruhi, how she kind of shapes, bends, and expands reality according to her imaginations and her desire. Keon's universe into what he considered to be real, what he considered to be out there. So this is what's going to be the focus for this part of the presentation. So there were some initial observations by scientist Titius-Bode where he identified a few nebulae moving away from Earth. Following these observations, we have the work by Edwin Hubble, who identified the distance of the nebulae and indicating that they were other galaxies. And following this, he also formulated the first equation of the rate of expansion of the universe. I'm pretty sure the plural of nebula is nebulae. Maybe it's not. That is what I have in my brain. Yeah. Okay. Yeah, Titius-Bode is kind of a weird name. Anyway, I get too distracted by the chat. I'm so sorry. So maybe just ask like questions. Yeah, nebulae. Yeah. Okay. So today I want to present the two main things that Edwin Hubble did, which was, first of all, identifying the distance of this nebulae, and secondly, formulating the first equation for the rate of expansion in the universe. And we'll look at that step by step, how he was able to do that. So first of all, what he did is that he looked at all these nebulae that were identified, and he looked at what is known as Cepheid. Cepheid variable stars. And these are stars that have a well-known relationship between their absolute magnitude, so it basically is their total luminosity, and their pulsation period. So stars basically become slightly dimmer, slightly brighter, slightly dimmer, slightly brighter. And for this type of stars, the relationship between these two is known very well. So you can look at their apparent magnitude, and that is the magnitude that you actually measure when you're looking at them. And you calculate the period of this dimming, becoming brighter, dimming, becoming brighter, which goes on for several days. This is obviously not a short process. But you basically look at the star for a given amount of time, and from this you can extract the period for a given Cepheid variable. Following this, you can look at these luminosity period charts and identified what was the period that you identified in the star that you looked at. And because the Cepheid variable stars have a very clear and the pulsation period, you can say, for example, oh, I measured 5.4 days, and you go here in your chart, you look at where you have 5.4 days in your Cepheid variable line, and you in turn also known the total luminosity. So from this you come out getting your apparent magnitude and the absolute magnitude. So from the apparent magnitude and the absolute magnitude, you can derive the distance at which the star is found. And this is done with the distance modulus formula right here. We'll not get into plugging numbers in there, etc., but I just want to give you a rundown of how Hubble was able to get these numbers. So Hubble measured the distance for a bunch of these stars, and from this he determined that these stars were actually very far away. And what he thought is that they're so far away that they must be outside the Milky Way. Given that they're outside the Milky Way, he said, okay, these are other galaxies. These are not just random nebulae that are found inside the Milky Way. These are other galaxies. So that is his first initial proposal. These nebulae are other galaxies found outside the Milky Way. And now we'll get to number 2, which is how did he measure that they are going away from us, right? How did he measure that they are expanding? So this was done by measuring the galaxy's velocities, and this is done with the method of measuring what's known as the redshift. So a given star has a fingerprint of what elements are found in the star because they have a certain wavelength at which they emit. This is like a fingerprint of I am hydrogen, I am helium, etc., etc. These stars that are far away, that are moving, you will actually see that these emission lines, that the wavelength of these spectral lines is not the same as if they are measured at rest on Earth. So you look at the difference between these two wavelengths that you measure, the one on Earth that is known and the one from the star that you capture. And from this you can compute something that is called the redshift. So how much is it shifted from what you measure on Earth? And objects that are moving far away are going to be redshifted, meaning that the frequency will be lower, and objects that are moving closer are blue shifted, meaning that the frequency is going to be higher. There's a little bit of a more illustrative explanation of how to calculate velocities via the redshift, which I just included right here. But in essence, this is the strategy that Hubble went about measuring the velocity of these stars and nebulae. So following this, this is the original publication by Hubble, where he plotted the velocity of these nebulae against the distance of the nebulae. So he had these two data points, and he just plotted everything. And just as a side note, this is the conversion from parsec, which is a unit of distance in astrophysics, to just meters. And this is the original paper by Hubble, where he found a linear trend between the velocity and the distance at which these stars were found. And this is what brings us to the postulation of Hubble's law. So he extracted a linear proportionality, which is the line that we see right here. He just fitted a line through all of these stars, or all the data of the stars. And he extracted a linear proportionality with a proportionality constant that was later named the Hubble constant. So this H0. Yeah. And then the equation that we actually see in the opening is a little bit of a reformulation of this equation, where you extract what is known as the Hubble time, which is the apparent time of the universe, just by looking at this expansion equation by Hubble. And this is just by rearranging, distance over velocity is time, and that would be 1 over Hubble constant. So there's a little bit of a debate of so now just quickly on the criticisms, in case anyone wants to, and if anyone has heard about this before, there are some criticisms regarding what the actual number of the Hubble constant is, particularly because the Hubble constant is not a constant and is actually a parameter that changes with time, because there are a lot of more expansion processes and not just what Hubble extracted. Basically, expansion of the universe is a process that compounds and is not just constant. So this equation is valid to some extent, but that is kind of everything in astrophysics. But yeah, so I don't know if you guys have questions in that, but I just wanted to Haruhi. And I interpret this as, first of all, I feel like they included a lot of equations that have a big H in them, and I think that is because of Haruhi's name. But also, I was considering the fact that I feel like Haruhi is kind of a component that expands the world around her. So in a sense, she's kind of like a Hubble constant in the show. So that was my interpretation of this. But yeah, so let me know what you guys think about that, and if you have any questions before we go on to the next part. How do we know that distance isn't increasing due to the universe expanding and not the gravitational force of something else? So for now, what we have talked about is not really what makes the universe expand, but rather what is the trend of universe expanding, and like what is the rate at which the universe is expanding? How much farther away do we see things becoming? And that is what Hubble was, that is the trend that Hubble derived, not really the cause, because when we get into the cause, it becomes a lot more complicated. And that is why this Hubble constant is not actually a constant. But yeah, so this equation doesn't really tell us the why anything is expanding or why we see things become like going farther away from us. Rather, it just tells us that they are, and that there seems to be a trend of a rate at which they are moving away. So I hope that answers the question. But yeah, let me know if you guys have any more questions. I don't know if I went a little bit fast on that. Just want to point out that I think this is a really beautiful graph for the types of graphs that you find from old scientists, or not, well, I guess old, almost 100 years old. But yeah, I feel like this is something that is very comprehensible. A very nice, just linear trend. But yeah, so if you guys are interested and have a little bit of time, there's the original paper that was published by Hubble back in the day. So, please let me know if you guys have any questions. Otherwise, okay, yeah, did he have to make the linear approximation by hand? I'm honestly not sure about what the processes were for doing that, but probably they just had like, you know, like line of least squares type of thing. I think I probably did that by hand once in my life for like biology. But we would certainly take a lot less time nowadays with like Python or something like that. Let me just I mean, it is a basic regression, but he had about 26 data points. So it's not that fun when you have a lot of points. But yeah, I mean, it's definitely doable by hand. I don't know if they had maybe something to make it slightly easier. Maybe they did. I am not exactly sure. Maybe they just put like PhD students to do this type of work. But yeah, so let me know if you guys have any more questions, because I actually only have one more equation to go over at the moment, because I thought I was gonna ramble for a long time. How much of this did I learn at university? So we never discussed the Drake equation. That is something that is a little bit more sci-fi. I had heard about it in like, you know, just science podcasts and things like that, but that is something that it's not something that physicists think about every day. The Drake equation is kind of like just a funny, interesting equation, just basically putting the thought of alien intelligence into an equation makes it seem fun. But yeah, Hubble's law, definitely something you look at your typical astrophysics lecture, which we did. We went a little bit more in depth in it. And the next one is actually one that I had actually never heard about. So and it is actually pretty interesting, because I will relate it to something else, but yeah. And yeah, a short and fun stream is better than a forced one. That is very true. I also feel like making it a compact 1 hour stream maybe makes it a little bit nicer as well. And we have some time to just talk about the future of the series after. So yeah, so the last equation that I want to discuss is the, sorry if I'm getting his name wrong, but Titius-Bode law. The Titius-Bode law. And this one is the one right here on the left. And this one is one that I had never actually heard about before, but it's actually a pretty interesting one. So the Titius-Bode law is a series that describes the distance of the nth planet, so planet number n, from the sun if the radius of Earth in orbit is normalized to 10, is given by the Titius-Bode law. So it's dn, so the distance of my nth planet, is equal to 0.4 plus 0.3 times 2 to the n. So if we say n is minus infinity, so the closest, it would be Mercury. If we say it's 0, then it's Venus. If we say it's 1, it's Earth, 2, Mars, etc., respectively. So here's a chart of the different radii, so the different distances from the sun that can be calculated using this Titius-Bode law. Pluto included, because it's a paper from 1970. And we see that the Titius-Bode law seems to coincide very well for Mercury. Then we see Venus, Earth, obviously perfect because it's normalized for Earth. Mars, pretty close also. Ceres, parentheses, because it's not an actual planet itself, but a planetary body. Okay, we see very close. Jupiter also extremely close. Saturn very close as well. But then we start getting a little bit murkier. Uranus is still very close, but Neptune and Pluto are both very, very far off. So at that point, people started thinking, this law maybe, especially because the law kind of just came about from someone playing with numbers. They were like, this Titius-Bode law seems to not be great for just any planet. So at this point, people started heavily criticizing it, especially because it came of playing around with numbers, playing around with series. But it seemed to be very accurate to some extent. So that really puzzled people. And that is why even to this day, people still look at, even at planets outside of the Milky Way. They will try to estimate their distances using the Titius-Bode law, even though it's something that is not widely regarded as a great method, but it seems to have something in it that makes it kind of accurate. So yeah, it's really just an interesting series that can be used to at least model to some extent the distances of planets. And that is something that I just wanted to primarily, obviously this has to do with aliens, yada yada yada, we discussed that, but primarily that this really ties into hi Siansu, thanks for following. Primarily that this really ties into quantization. So it's a very beautiful analogy between quantizing the distances of the planets orbiting the sun to quantizing, the different orbitals, or however you want to call it, in an atom. So this is something that we'll talk about a lot more next week, because next week we're going to be talking about quantum physics. So this was my tie-in for this last part. So I generally just found this to be a very interesting law, as in that it's something that they tried to do. As you guys can see, this was okay, I didn't put the date. This is something that was first proposed in 1766. So that was about 150 years before quantum physics and before the Schrödinger equation, which is absolutely astonishing to see such a noble attempt to quantize the orbits of planets so much so much before they actually successfully quantized really small scale physics. So that, I feel like that is a very deep connection between these two things, even though the Titius-Bode law, like I mentioned, is not really considered mainstream astrophysics, so to say, as in that it's considered a little bit bogus in the way it came about and the way that it doesn't really have a theoretical sound base behind it. So yeah, please feel free to ask any questions regarding anything that we discussed. This is all that I wanted to present for today, and like I mentioned, I want to talk about quantum physics next week, which I personally find to be the most interesting part, and there'll be plenty of stuff to discuss. Is this the case of not having something better? To an extent, yes, because of the fact that it's still to this day considered to be a model of, because it gets very, like just looking at the background behind all of these calculations, maybe you guys have heard about 3-body problems and n-body problems. You can to a high accuracy calculate a two-body problem. So the Earth orbiting the sun, for example. However, once you start adding other planets, the gravitational pulling of other planets, of Earth, of the sun, of other everything around us, it's very have a clear understanding about distances and be able to estimate distances. Hi Dunder Bitchil. Thanks for following. So these are very complicated problems with no clear model to estimate. And this was kind of a random series that came about, which has no theoretical background to it. So in a sense, it's like saying, well, I found this series that can estimate a bunch of planets. I found this series that can estimate a bunch of planets. You have nothing else. You have nothing else. And even to this day, it's kind of considered a little bit bogus because of that, but still not completely worth throwing away because it was so accurate to some point. Bring up countable additivity. I'm not sure what that is. Maybe you can rephrase that. I'm not sure what exactly that is. God reusing code. Yeah, I mean, it would honestly be very beautiful to actually find a true quantized connection to planetary orbits. I think that would be anyone's dream. But yeah, but sorry to disappoint you guys. But I promise next week will be very interesting with all the quantum physics stuff that we'll discuss. Is everything you talked about useful in what you study? I'm in the third year of my studies. I finished physics in the first semester. The only useful laws that I currently use are laws related to electronics and sound. So for me personally, I don't study anything that has to do with astrophysics. It maybe was one of my least favorite subjects when I did my undergrad, but it's still interesting. It's still relevant to not isolate yourself from all other research, and to, have a little bit of an understanding about what's going on in different fields. But I definitely don't study anything currently in my master's that has anything to do with astrophysics or anything that I discussed today. But it's good to not be completely ignorant on other fields in physics. It's the one probability equation in the opening. Probability equation in the opening. There's a bunch of probability equations in the opening. I guess because everything, all the quantum physics equations have some probability in them. Okay. Let's see. Let's see if I can figure out which one you were talking about. Okay. Maybe you can send it to me, but I'll be discussing all of the equations that are shown in here. There is only one that I genuinely have no idea where it came about. So, yeah. But yeah, so let me know if you guys have any other questions. It's kind of useless to just put this up because I can't pause it apparently. But yeah, we're gonna be discussing lambda particles, positronium, etc. This is a lot more closer to what I am doing, so I hope to bring a little bit of an insight. And bye, Evangelion. Thank you for coming. And yeah, the Euler product equation was very weird. I agree. I have no idea where that came from. So that one I'm leaving that up to the mathematicians that want to take up the challenge of finishing this off. But yeah, I hope you guys found this kind of insightful and enjoyed it. So let me just go back to this. So I hope you guys found that kind of insightful, kind of interesting, and yeah. So more questions. I'm the math major, so I'll pretend to know how it works. Please. please, take on the mantle. Please tell me what the heck that is. I have no idea. A bit unrelated, but has someone applied the Drake equation to the current observable universe? Yes, and in fact, like I mentioned, there are a lot of different solutions for n, because so many of the parameters are just complete guesses, and have really, really incredibly huge uncertainties. So if you go through the sources, so like I said, I posted the presentation on Coffee. You can go through the sources that I posted. Some of them have some estimates as to what n could be using different models of star formation, different ideas as to how many planets are in the Goldilocks zone, etc. And you can find a really wide range of estimates. I believe there were also some up in the Drake equation Wikipedia. So definitely go and check that out if you're interested in some actual numbers. I just personally didn't want to put any specific numbers because I just honestly didn't have the time of going number by number to, just corroborate what they were putting up and understand why they were putting each number up. So I honestly just didn't feel comfortable putting that up if I was not sure that I could explain it. But if you guys are interested in some precise numbers and how they came about, there are a lot of sources where you guys can find that with the current knowledge that we have. I actually never thought about it when watching Haruhi. So yeah, I also when I just watched the opening and I just thought, has anyone documented the equations in this background? No, and I just thought, I feel like it's a worthwhile project to just have a look at that and have a look at if we can relate this to certain themes and maybe shed some light into why they even picked these out of like the thousands of equations that you can find everywhere. As a humanist, I don't feel very smart right now, but your explanation helps. Well, if there was anything that's unclear, you can feel free to DM me. I will also post this the video on demand on YouTube, and if you guys have any questions, you can also maybe tell me timestamp, like what do you mean by this, etc. And I can do my best to help. As a software engineer, I have been put into my place. I don't know. I am not the programmer type, so I admire all the software people. I can barely just use Python for like plotting stuff. That's the only thing I can do. So, to each their own. So I hope you find the explanations here helpful. I have seen the Haruhi problem. Also more of a very in-depth math thing, so I don't know if I could explain it myself, but if you guys are interested, I can definitely give it a try. Yeah, I mean, math is hard. Math is really hard. So that's why today I wanted to keep it a lot more conceptual, taking everyone step by step as to what these equations mean. You just see a bunch of numbers. Yeah, what does this even mean? What does this even mean at all? As an unemployed computer science major, I now subscribe to Haruhism. So true. um, and yeah, a lot of science is theory and conjecture, yes. And in the end, I just, I feel like physics is a great field where a lot of insane math and a lot of practical work is taken together to, be like a little bit more of a realist understanding of the world. And that's why I really appreciate these more conceptual understandings, especially for people that are completely just not in the field, but are actually interested in just getting a little bit of a peek about what all of these things mean, what it means to be in physics at all. And yeah, Haruhi problem mentioned super mutation, my beloved. Super permutations, my beloved. Yeah, obviously. I obviously love permutations. No, that was like literally just horrifying. Like, it just reminds me of like every theoretical lecture that I had to have. Like, I used to think that I could just be like theoretical physicist. Honestly, embarrassing. I could never do that. But anyway, I hope you guys found this somewhat insightful. And I hope there was a bit of a at least you got something out of the stream. And if you guys have any feedback as to what could be improved, what was not explained as clearly, etc., etc., please just let me know, because this is something that I would really value for the article that I would like to post alongside the end of this little series that I'm trying to do. So this will likely be a 3 or maybe 4-part series. I'm not sure how I'm gonna end up splitting it up. But the rest of the series will follow a similar sort of a similar rhythm, as in we're gonna go equation by equation, talking about what it means, maybe having to see a little bit of a background, particularly with a lot of the quantum physics stuff where there's a lot of symbols that kind of have to be explained. But I hope you guys found this somewhat insightful. Yeah, I use my real hair also particularly because, when I'm explaining stuff, first of all, I'm a little bit nervous, I will admit. And second of all, I want to focus more on what I'm explaining. So if I have a wig, I'm gonna be focused on like getting the wig out of my eyes and stuff. So it was definitely more comfortable to just use my real hair. But yeah, if you guys are interested, go download the presentation. It's in my Ko-fi and my Twitch page, and you can go over some Fermi problems. You can go over the examples that I listed on calculating velocities via the redshift, etc. If you guys are interested. My YouTube is also Pikachurin. I will post it. I will link it after this. I'll link it to my profile over here. But yeah, I will post the video on demand over there if you guys are interested in rewatching this, posting any particular questions, etc. And yeah, I'm glad you guys enjoyed this. It's gonna be a fun project, I think. I may do other anime in the future as well. And yeah, and thanks everyone for watching, and I'll see you guys next week. So